Hey folks, welcome to this episode on equilibrium expressions. So, let's start off right away. Law of mass action. When we look at a system in equilibrium, the concentration of the reactants and the concentration of the products remain constant. Remember, as we saw in our previous lesson, that they're not necessarily the same concentration, but they do remain constant in terms of their relative amounts. Now, experimentally, it's found that the ratio of the concentration of the products and the reactants is constant at a particular temperature, and this constant is called the law of mass action. Now, we can see this in this little diagram over here, where we compare our concentration of products to our concentration of reactants, and we call this KEQ. Now, this KEQ is our equilibrium constant, and that's what we call this ratio between our concentration of our products and our concentration of reactions. Again, that is called our KEQ, or our equilibrium constant. So this equilibrium expression takes into the law of mass action, which again states that the system at equilibrium at a given temperature is found to be the ratio between our products and our reactants. So in this case, we have our products C and D and our reactants A and B. So just like we saw on the previous slide where we had KEQ is equal to the products over our reactants, we've now blown that up a little bit and made it a little bit more specific, where we have the concentration of our products raised to their coefficients divided by the concentration of our reactants raised to their coefficients, and this remains a constant as long as temperature remains constant as well. Now in this case, when we look at here, the A, B, C, D in the uppercase, those are concentrations of our species, and the A, B, C, D are the coefficients in our balanced equation. And once again, this is called our equilibrium constant, or KEQ. Now, KEQ, we'll see later on in this lesson, is just a general expression for a whole bunch of different things. We can look at concentration, we can look at pressures, we can look at a whole bunch of other different things. So we're going to differentiate KEQ a little bit more as we go on. Now, one of the main things to remember is that in this KEQ, in the equilibrium expression, that these concentrations of our products and reactants are raised to the exponent which is equal to their coefficients of their coefficients in a balanced equation. This, a lot of people get confused with because they remember the rate of reaction expression, the rate expression, where the exponents are found experimentally. In this case, these coefficients are determined by the balanced equation. Now, when we look at this, depending on how many reactants or products we have, the units will actually change. And so, because they don't really have any particular meaning in terms of the KEQ value, we look at more the magnitude, aka the how large that number is. That has more meaning than the actual units. So in KEQs, we don't really show them. This is probably one of the only times where you don't need units even though you're working with them. So let's look at an example here. Here we have a following reaction. We have H2 gas reacting with I2 gas to create 2 moles of HI gas. This is performed 3 times in a closed container at the specific temperature, and the following data was collected. So we have 3 trial runs, 1, 2, and 3. Now it started off initially in different scenarios. In our first trial, we had 2 moles of 2 mole per liter molar of H2 and 2 molar of I2. In our second trial run, we wanted to see if we'll establish equilibrium if we start off with our product rather than our reactant. So we start off with 2 molar of this, and then here we mixed it up a little bit. We started with 0.01 and 0.35. So first of all, let's determine the equilibrium expression for this reaction right up over here. So remember that K equilibrium is equal to the concentrations of our products over the concentration of our reactants. Okay, so we just put that in square brackets. So in this case, we have to look at our products, and our products are going to be our HI, and our reactants are going to be our H2 and our I2. So our K equilibrium is going to be equal to the concentration of our products, which is HI, and this is a gas, raised to the exponent of its coefficient, so 2. Okay, and that's going to be over the concentration of the reactants raised to their coefficient. So here we have H2, and this is going to be a gas. Now the exponent in H2 is just 1, so we can leave that as that. We can assume the 1 times the I2 gas, square brackets, again the coefficient of 1, so we leave it as that. So that is our equilibrium expression for this reaction. Now let's calculate the value for KEQ. So how do we calculate the value for KQ? We simply take this run and we put them in. Okay? Now these are our initial concentrations over here. This value is looking at K equilibrium. It's looking for the ratio of products to reactants, not at the initial concentration, but actually at equilibrium. So we have these values, that's what we started with, and this reaction happened, and eventually we got to a point where there was no changes in the concentrations, and these were the values that we got. So because this is looking at the ratio between products and reactants at equilibrium, we're not going to use these values here, we're going to be using these values over here. So if we plug these in, if you plug this into our equation, so let's do for trial number 1, for our KEQ, we have HI, which is going to be 3.116, and that's going to be squared, divided by the concentration of H2, which is going to be 0.442 to the power of 1, so we can just leave it as that, times 0.442, and the value that we get here is 49.8. Now, if we look at trial number 2, okay, that's going to be KEQ, so we're going to use these values over here. We get 1.560 squared divided by 0.221 multiplied by 0.221. So again, we're just using the values of our H2 and our I2, and we're just plugging them into this equation. And if you do the calculation here, you get 49.8. Finally, if we do the third calculation, the third trial, or the values for their third trial, we have 0.280, and that's again squared, divided by 0.035 multiplied by 0.045. Now if we do this, again, we get 49.8. So what this is showing us is that the value of K is the same, assuming that the temperature is the same, even though we might have different starting values. So the size of our K equilibrium tells us a little bit about the reaction. So once again, our KEQ is just a ratio between our products and our reactants in terms of concentrations. If our KEQ is large, that means the products are favored. So let's take a look at that. For KEQ to be large, our numerator has to be huge and our denominator really, really, really small. And so when we have this ratio, for example, if we had 10 over 1, that would give us a ratio of 10. That's a pretty big number compared to if I did 1 over 10. In this case, KEQ is large. Now what does this mean? Well, remember that this is the concentration of products over reactants. So at equilibrium, again, because this is K equilibrium, it's looking at the ratio between this at equilibrium. At equilibrium, the relative amount of my products to my reactants is big. And so we call this, that this reaction at equilibrium is product favored. It will go into the direction of creating more products. So let's say, for example, we had A plus B giving us C and D, C plus D, and this was a two-way reaction. If this was product favored, this reaction would be mostly going to the right, okay, and producing those products. Now, what if KEQ was small? And the only way that KEQ would be small is this if our denominator was much larger than our numerator. So in this case, 1 over 10, for example. So this would give us a decimal, and that decimal would obviously be KEQ, and if KEQ is small, what we'd say is that the reactants are favored. What that means is that, again, going back to this reaction between A plus B giving us C plus D, this reactants, the A plus B reacted and gave us C plus D, but then C plus C and D reacted to give us A and B. And this would eventually go back and forth, but at equilibrium, where this would lie, it would lie more in the direction of this. More reactants would be reformed. And so at equilibrium, we would have a larger amount of reactants than we would have of products. Now, if KEQ is equal to 1, that means that the concentration of our products and reactants are the same, and so at equilibrium, there's no difference. Their relative abundance is basically the same. So once again, this magnitude tells us a lot about the ratio. This little slide just allows us to give a little bit more detail in terms of these numbers here. If we have a really big KEQ times 10 to the power of 10, we can say that the reaction has really just gone to completion. So what that means is that when we look at A plus B, we don't really need a two-way arrow. We know that it's basically all of A and all of B have been converted into C plus D. So because KEQ is so big and KEQ says that it favors the formation of products, at equilibrium we're going to have a huge amount of products, basically meaning that we have converted all of our reactants into products. On the other hand, if we had our small KEQ and we had a really small one, less than times 10 to the negative 10, what we can say is that, even though A and B reacted, let's use some different variables here. O plus P gives you R and plus S. So even though these two reactants reacted and they maybe created some products, these products didn't stay. They reacted again and formed the original reactants. So this reaction would lie to the left, almost making it like it didn't actually even happen. Even though there might have been some interplay between these to create these, and then these creating this, and there might have been some equilibrium, at the end of this reaction, we would have a higher concentration of our original reactants than we would have of our products. Now, there is an exception to our equilibrium expression. Our equilibrium expression does not contain solids or pure liquids. Now, the reason for that is because they're pretty much incompressible. And because that's the case, the concentration doesn't actually change. When we look at solids, the concentration of a solid is determined by the density. If we look at something, for example, like water, in terms of a pure liquid, well, the concentration doesn't change either. Let's say we had a glass of water, and this glass of water had 55 mole. Now, if we added more water to this water, we're not really changing the concentration, because as we increase the volume of water, we're also increasing the amount of moles of water at the same time. So we can't change one without the other. In terms of water, because it's a pure liquid. The pure liquid is pure. It's as we add our volume, we also increase our moles. If we take away moles, we're taking away volume. So they're pretty much incompressible, solids and liquids, so that we don't actually include them in our equilibrium expressions. So when we look at this homogeneous equilibrium, remember the homogeneous equilibrium means that all the species, the reactants and the products, are in the same state, gas, gas, and gas. If we were to create the equilibrium expression for this, well, let's look at our general equilibrium expression. KEQ is equal to the concentration of our products over the concentration of our reactants. Now, if we make this a little bit more specific, we get concentration of A to the power of A, concentration of B, let's change these variables. If we look at a reaction like A plus B gives us C plus D, so that this would be the concentration of C to the power of C, concentration of D to the power of D, because these are our products, C and D, over the concentration of our reactants, concentration of A to the power of A, and concentration of B to the power of B. Again, those A, B, C, D would be the coefficients of their balanced equation. Now let's apply this general equation into the equation that we have here. Our product is ammonia and our reactants are H2 and N2. And because they're all in the gas state, we can include them all into our equilibrium expression. So what we'd have is we'd have the concentration of NH3 in the gas phase to the power of 2 over the concentration of H2 gas to the power of 3 multiplied the concentration of N2 gas to the power of 1. But because it's 1, we can leave it out. So our K equilibrium expression, or our equilibrium expression for this reaction, is this right here. Now, when we have these heterogeneous equilibriums, or equilibria, that have species in different states, here we have gas, gas, and liquid, we have to change it a little bit. We can't include these pure substances because they are basically incompressible. And therefore, because we can't because we can't actually change the concentration of these pure liquids or solids, we actually get rid of them. So at the end, what we end up getting is we just look at the ones that we can change. And so our K equilibrium for this reaction, in this case we have liquid water that decomposes into hydrogen and oxygen gas, or we go in the reverse direction, we have oxygen and hydrogen turn into liquid water, what we're going to see is that all it is going to be the concentration of H2 gas to the power of 2 multiplied by the concentration of O2 gas to the power of 1. We don't include the water because its concentration will not change because it cannot be compressed. So here's what we were saying about the KEQ taking on a whole bunch of different formats. A lot of people get confused with this because textbooks and individuals use these interchangeably. Yes, they are, but in terms of what they mean, that can be a little bit different. So we have KEQ, which is basically our general expression. It's basically like saying money. We don't say what currency is, but we can have the euro, we can have Canadian dollars, we can have US dollars, we can have yen, we can have Polish zloty, we can have Turkish lira, whatever. So the money in this case is the KEQ, or maybe a better way of saying currency. We can have many different types of currencies, and as we go with KC, KP, KSP, we're specifying which type of currency. When we look at KC, this is talking about concentration, P, partial pressures, SP is the solubility product, K is a weak acid, B is a weak base, and here we have the auto-ionization of water. Now you can see that most of them are very similar. We look at the relative abundance of our products over our reactants. Same thing if we look at pressure over here, and same thing over here. If we look at a weak acid, here we have our hydronium ions over here, we have our H plus and our O's as well. So when we look at this, you can see that the relative abundance is going to be very much the same. It's just the way that we actually express this. So regardless of how, in terms of Kc, the general K equilibrium is the same as the Kc equilibrium. It's the concentration because Kc looks at concentration, and this is primarily what we use, so we usually equate it to K equilibrium. So Keq, Kc will give us the same format in terms of our looking at our ratio between our products and our reactants. Now, when we want to look at Kp, now sometimes it's easier to express our equilibrium constant as a Kp for homogeneous systems that are in gas format rather than molar concentrations, because gas are more easily expressed in pressures rather than concentrations. And so we have to actually convert our Kp and our Kc. Now we can use this equation over here to do that. So we can look at our relationship between Kp and Kc. Again, R, when we look at R, it's our gas constant, T is our temperature, and delta N is the sum of the coefficients of our gas products minus the sum of the coefficients of our gas reactants in the balanced chemical equations. So I'll say that one more time. When we look at N, it's the sum of the coefficients of our gas products minus the sum of the coefficients of our gas reactants in our balanced chemical equation. So we can use this equation to convert from one form to another, and then we can use into this equilibrium expression. So again, our K equilibrium, particularly when we're looking at partial pressures, is going to be denoted by Kp. Here's the partial pressure of C raised to the power of its balance coefficient times the partial pressure of D raised to its balance coefficient over the partial pressure of A raised to its coefficient, and the partial pressure of B raised to its coefficient. All right, folks, that's it for this episode. We'll see you soon.